Prove using the principle of mathematical induction. Let me call this statement we call P of n. Statement for natural numbers 1 into 3, 3 into 5, 5 into 7 plus up to 2n minus 1 into 2n plus 1 equal to n into 4n square plus 6n minus 1 upon 3. This is statement for n natural number. N is any natural. Now to prove this statement, first part, for n equal to 1, we are going to show that statement is true for n equal to 1. So for n equal to 1, we show left hand side is equal to right hand side. Left hand side, say 1 into 3. Beginning from this number 1 into 3. This is the beginning. Now complete at a number which is obtained by putting n equal to 1 here. So put here n equal to 1. So 2 into 1 minus 1. That is 1 into 2 into 1 plus 1, that is 3. So 1 into 3. So begin from 1 into 3 and at 1 into 3. So beginning is the ending. So LHS is 1 into 3 only, that is 3. And RHS, putting here n equal to 1. 1 into 4 into 1 square is 4. 6 into 1 is 6 minus 1 upon 3. So this is n minus 1, 9 by 3. 9 by 3, that is 3. So LHS is equal to RHS. So this is true for n equal to 1. Statement is true for n equal to 1. Now, second part. We suppose that statement is true for n equal to k. So let P of k be true. That we accept without proof where k belongs to n. So putting here n equal to k, statement is 1 into 3, 3 into 5, 5 into 7 plus 2k minus 1 into 2k plus 1 equal to k into 4k square plus 6k minus 1 upon 3. So this statement n equal to, for n equal to k, this is true. It is true, that we accept without proof. So this is true, accepted. Now using this, we show proof for n equal to k plus 1. Now I am writing this statement for n equal to k plus 1. So left hand side, beginning from left hand side. So left hand side is, see, 1 into 3 plus 3 into 5, 5 into 7 plus up to here, replacing n by k plus 1. N is replaced by k plus 1. So left hand side for n equal to k plus 1. See here I have taken n equal to k plus 1. Here n equal to k plus 1. So it is left hand side for n equal to k plus 1. So it is equal to 1 into 3, 3 into 5, 5 into 7. Now look, its simple form is 2k plus 2 minus 1, that is 2k plus 1 into 2k plus 3. Now by observation, We put here second last term. We are putting now this second last term. Second last term, it will be in this space. By observation, second last term is here. So we make up here second last term. For that, observe this series. See, coming back. See, this is 7. So in previous step it is 5, then 3. So difference of 2 units. Coming back, you can see that here there is difference of 2 units in second place. Observe first place 5, this is 3, this is 1. So in both values, coming back, there is difference of 2 units. Every time 2 units are decreasing. So here this value will be 2 less than this number. So subtracting 2 from this number, this will be 2k plus 1. And similarly, subtract 2 from this number, this will be 2k minus 1. And so second last term we always put by observation. And after putting second last term, every time if you observe this part till second last term, its value will be always in equation 1. You can see that it is ditto. So now we are finding this value here. So therefore, it is equal to k into 4k square plus 6k minus 1 upon 3 plus 2k plus 1 into 2k plus 3. Now we simplify this. Simplifying this, it is equal to k into 4k square plus 6k minus 1 plus 3 into, we multiply 3 with this product, and that product is 4k square, 2k into 2k, 4k square plus 6k plus 2k, that is 8k plus 8k plus 3 into 1 is 3 upon 3. So simplifying this, k into 4k square, so 4k cube plus 6k square minus k plus 3 into 4, 12k square plus 24k plus 9 upon 3, that is 4k cube plus 6k square plus 12k square, that is 18k square plus 23k plus 9 upon 3. Now look here. Say this is unique polynomial. If you check sum of coefficients of terms with odd power and sum of coefficients of terms with even power, look here. 4, that is coefficient of x cube. This is coefficient of k. So coefficients of terms with odd power is 4 and 23. Their sum is 27. And then sum of coefficients of terms with even power 18 and 9, total is 27. So sum of coefficients of terms having odd power is equal to sum of coefficients of terms having even power. So its one factor is k plus 1. K plus 1 is its one factor. Now to find the other factor, here k plus 1 is a factor, so we take here minus 1. Then taking here coefficients 4, 18, 23, 9. K plus 1 is a factor, take here minus 1. Now put 0. Vertical addition. Diagonally multiplication. -1 into 4 is -4. Then vertical addition. Diagonally multiplication. Well, -1 into 4 -40. Vertical addition 9. Diagonally multiplication. Here this is 0. So this will be, say this was coefficient of k cube. This was k square. This was coefficient of k. This was coefficient of 1. Now after putting a factor k plus 1, other factor is 4k square plus 14k plus 9. 4k square plus 14k plus 9 upon 3. Now this term we keep as it is. Now we take right hand side. Right hand side for n equal to k plus 1. For n equal to k plus 1, this is simple form of left hand side. Now simple form of right hand side. So put here n equal to k plus 1. Then 4 into k plus 1 whole square plus 6 into k plus 1 minus 1 upon 3. In so many questions, beginning from left hand side, developing terms, at last continuing the calculation, we get equal to RHS. So beginning from LHS, we derive RHS. But in some of the questions, simplify LHS, keep inside, then take RHS. In RHS, put n equal to k plus 1, simplify it separately. So simplification of LHS and RHS separately, show their simple form equal. So LHS equal to RHS. You can also prove by this way. So here we are simplifying individually LHS and RHS. So now in RHS we have taken here k plus 1, here k plus 1, here k plus 1. Now simplifying this, k plus 1 into 4k square plus 8k plus 4 plus 6k plus 6 minus 1 upon 3. That is equal to k plus 1 into 4k square plus 14k plus 6 plus 4, 10 minus 1 is 9 upon 3. And you can see that from result 2 and 3, from 2 and 3, it is clear that LHS equal to RHS for n equal to k plus 1. So this was proof for n equal to k plus 1. So P of k plus 1 is true. Therefore, P of k is true implies P of k plus 1 is true. So statement is true for n equal to, for any natural number n. For every natural number n is true. Prove using principle of mathematical induction. New question. Let Pn 1 by 2 plus 1 by 4, 1 by 8 plus 1 by 2 raised to n is 1 minus 1 upon 2 raised to n. This is statement for natural numbers. First part, for n equal to 1. For n equal to 1, left hand side is 1 by 2, beginning from 1 by 2. Now put here 1. So end will be at 1 by 2 raised to 1. That is 1 by 2. So beginning is 1 by 2 and will continue till you get 1 by 2. So beginning is the ending. 1 by 2. RHS is So LHS is equal to RHS. So P of 1 is true. Now second part, second condition. Let P of K be true. So we repeat this statement for n equal to k. So 1 by 2 plus 1 by 4 plus 1 by 8 plus up to 1 by 2 is to n is 1 minus, here we replace n by k. 1 minus 1 upon 2 is to k. Say this is 2 square, this is 2 cube, this is 2 raised to 1. So continuing this is 2 raised to k. So we shall use this in the proof for n equal to k plus 1. So for n equal to k, LHS equal to RHS is true. We accept without proof. Now proof for n equal to k plus 1. So proof for n equal to k plus 1. Now I think here n equal to, we replace k plus 1. So beginning from left hand side for n equal to k plus 1. So 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 2 raised to k plus 1. Now as we do in every question, 1 by 2, this is 1 by 2 square, this is 1 by 2 cube, that is 4, that is 8, it is 1 by 2 raised to k plus 1. Now by this observation, coming back, it is 2 cube, this is 2 square, this is 2 raised to 1. So here 1 power will be decreased. So 1 upon 2 raised to k. So this we put by observation, second last term. So after putting second last term, every time if you observe this part till second last term, then always you will find its value in equation 1. So now we substitute this value in this part. So it is equal to 1 minus 1 upon 2 raised to k plus 1 upon 2 raised to k plus 1. Now we simplify this. We want RHS. In RHS, we want to replace n by k plus 1. So this is required. In place of n, we want to set k plus 1. So RHS for n equal to k plus 1. Now we are at here and we are going to join this term into this term with sign of equality. So 1 minus, now say this is 1 upon 2 raised to k. This is 1 upon 2 raised to k into 2. 2 raised to k plus 1 is 2 raised to k into 2 raised to 1. Now 1 minus 1 upon 2 raised to k common. So here 1 is left, here minus 1 upon 2. So it is equal to 1 minus 1 upon 2 raised to k into 1 upon 2. And say it is derived. This is 1 minus 1 upon 2 raised to k plus 1, and it is equal to RHS. Therefore, LHS equal to RHS for n equal to k plus 1. For n equal to k plus 1, LHS equal to RHS. Therefore, P of k plus 1 is true. Therefore, P of k is true implies P of k plus 1 is true. Therefore, statement is true for every n belonging to n. Prove this result using the principle of mathematical induction. That P of n, A plus AR square plus AR raised to n minus 1 equal to A into R raised to n minus 1 upon R minus 1. This is P of n. N is natural number. Now first part, for n equal to 1. For n equal to 1, left hand side is, say putting here, beginning from first term, LHS for n equal to 1, beginning from A, continue sum till term which is obtained by putting here n equal to 1. So if you keep here 1, so R is to 1 minus 1, R is to 0. So A into R is to 0 is A. So first term itself is the last term. So LHS is A and RHS is, putting here A equal to 1, n equal to 1. So it is again A. Therefore, LHS equal to RHS. Therefore, P of 1 is true. Second part. Let P of K be true. Suppose that statement is true for n equal to K. Therefore, writing this statement by putting n equal to K. So A plus AR plus AR square plus AR raised to K minus 1 equal to A into R raised to K minus 1 upon R minus 1. This we accept without proof. Statement for n equal to K. Now, proof for n equal to K plus 1. So, in left hand side, writing left hand side for n equal to K plus 1, I am putting here K plus 1. So, A plus AR plus AR square plus AR raised to, put here K plus 1 minus 1 as it is. So this is A plus AR plus AR square plus AR raised to K plus 1 minus 1, that is K. Now as we do in every question, what is second term from last? We make up here. So second term from last will be, observe this sequence. See, coming back, E is constant. Power of R is decreasing by 1. So here E constant, power of R, it will be decreased by 1, K minus 1. And when you put second term from last, you will find a value of this part in equation 1. So here it is its value. So it is equal to putting this value A into R raised to K minus 1 upon R minus 1 plus A into R raised to K. So here equation result 1 is used. Now we are simplifying this and going to derive right hand side for n equal to K plus 1. So we want RHS with here K plus 1. So simplifying accordingly, here LCM is R minus 1. So A into R is to K minus 1, R minus 1. That is A into, now expanding this, A into R is to K minus A plus A into R is to K plus 1. Multiply this inside. R is to K into R is to K plus 1 minus A into R is to K upon R minus 1. This will be cancelled. Now this is positive. A into R is to K plus 1 minus A upon R minus 1. Taking A common, r is to k plus 1 minus 1 upon r minus 1. And you can see that, say, n is replaced by k plus 1. So this is RHS for n equal to k plus 1. It is equal to RHS. Therefore, LHS equal to RHS. So P of n, P of k plus 1 is true. Therefore, P of k is true implies P of k plus 1 is true. Therefore, Pn is true for every n belonging to n. Prove using principle of mathematical induction. Let me call this statement P of n. P of n 1 plus 3 upon 1, 1 plus 5 upon 4, 1 plus 7 upon 9, 1 plus 2n plus 1 upon n square equal to n plus 1 whole square. First part, for n equal to 1. For n equal to 1, left hand side, say this is first term. We continue this product up to the term which is obtained by putting here n equal to 1. So keep here n equal to 1. What is the output? 1 plus 3 upon 1 square. 1 plus 3 upon 1 square. And say 1 plus 3 upon 1 square. It is first term. First term is itself last term. So beginning is itself ending. Putting n equal to 1, we are getting this number. So beginning first term itself is the last term. So it is equal to 4. And RHS is putting here n equal to 1. This is 4. So LHS is equal to RHS. So P of 1 is true. Statement is true for n equal to 1. Now second part. Let P of k be true. Statement is true for n equal to k. So we put this statement for n equal to k. 1 plus 3 upon 1. 1 plus 5 upon 4, 1 plus 7 upon 9, 1 plus 2k plus 1 upon k square, k plus 1 whole square. So this statement I have written by replacing n by k, and we accept this without proof that this is true. Now for n equal to, proof for n equal to k plus 1. So in left hand side I replace here k plus 1. Beginning from left hand side by putting k plus 1. So LHS is 1 plus 3 upon 1, 1 plus 5 upon 4, 1 plus 7 upon 9 up to 1 plus 2 into k plus 1 upon k plus 1 whole square. So n is replaced by k plus 1. So it is equal to 1 plus 3 upon 1, 1 plus 5 upon 4, 1 plus 7 upon 9, and this is 1 plus 2k plus 3 upon k plus 1 whole square. Now here, as we do in every question, we make appear here second term from last term. From this dot, we make second term from last visible. So by observation, look here, 1, 1, 1. So this will be 1. Then look here, this is 3 square. This is 2 square. Here it is 1 square. 3 square, 2 square, 1 square. So here this is k plus 1 square. So this will be k square. Look here, 7, 5, 3. So in numerator in second term, there is a difference of 2 units. Coming back, 2 is decreased. So from 2k plus 3 minus 2, that is 2k plus 1. And doing this, you can see that we have obtained ditto expression which is in equation 1. So now here I replace k plus 1 whole square. So it is equal to k plus 1 whole square into 1 plus 2k plus 3 upon k plus 1 whole square. Now simplifying this, k plus 1 whole square, here k plus 1 whole square plus 2k plus 3 upon k plus 1 whole square LCM, this will be cancelled. So it is k square plus 2k plus 1 plus 2k plus 3. This is its simple form. So it is equal to k square plus 4k plus 4, and this is k plus 2 whole square. Now look, we want here, we need here k plus 1, RHS for k plus 1. So here say we are going to have that expression. So now this 2 split up as 1 plus 1. K plus 2 can be expressed as k plus 1 plus 1. So see, in place of n, k plus 1 is derived. So this is RHS. So LHS is equal to RHS. Therefore, P of k plus 1 is true. Therefore, P of k is true implies P of k plus 1 is true. Therefore, statement is true for n equal to 1n. For every n belonging to n. Using the principle of mathematical induction, we prove this question. Let P of n 1 upon 1 into 4, 1 upon 4 into 7, 1 upon 7 into 10, plus 1 upon 3n minus 2 into 3n plus 1 equal to n upon 3n plus 1. First part, for n equal to 1. For n equal to 1, left hand side is, beginning from this number, we continue up to a number which is obtained by n equal to 1 here. So if you keep here n equal to 1, so this will be 3 minus 2, 1 into 4. So beginning from 1 upon 1 into 4, we continue till 1 upon 1 into 4. So beginning is itself ending. So left hand side is 1 upon 1 into 4. So it is 1 by 4. Right hand side putting n equal to 1, it is also 1 by 4. So LHS is equal to RHS. So statement is true for n equal to 1. Second part, let P of k be true. We suppose that statement is true for n equal to k. So replacing n by k in this given given statement 1 upon 1 into 4, 1 upon 4 into 7, 1 upon 7 into 10, 1 upon 3k minus 2 into 3k plus 1 equal to k upon 3k plus 1. This is true, that we accept without proof. And using this, now we are getting proof for n equal to k plus 1. So left hand side, beginning from left hand side for n equal to k plus 1. So now I keep here n equal to k plus 1. So 1 upon 1 into 4, 1 upon 4 into 7, 1 upon 7 into 10 plus, now here 1 upon 3 into, now n I replace by k plus 1. Again k plus 1. N is replaced by k plus 1. See, look here. This is k plus 1. N equal to k plus 1. So that is 1 upon 1 into 4, 1 upon 4 into 7, 1 upon 7 into 10 plus here. This is 3k plus 3 minus 2, that is plus 1. 3k plus 3 plus 1, that is 3k plus 4. This is last term. Now as we do in every problem, we make appear second last term. What will be the second last term? That we are making visible something into something. Here it is hidden. We are making it appear. So by observation, see, first value, look first value. Coming back, see here, 7 minus 3, 4. 4 minus 3, 1. So we have to subtract 3. 3k plus 1 minus 3. So it will be 3k minus 2. Then look here, 10 minus 3, 7. 7 minus 3, 4. So difference of 3 units. So similarly in second value, subtract 3. Removing 3 from this value, this will be 3k plus 1. And we are getting same number which is here. So it is equal to, its value is k upon 3k plus 1. Its value from equation 1. This term as it is 1 upon 3k plus 1, 3k plus 4. Now 1 upon 3k plus 1 common. So into bracket k plus 1 upon 3k plus 4. That is 1 upon 3k plus 1. Here LCM is 3k plus 4 will be multiplied with k. So it is 3k square plus 4k plus 1 upon 3k plus 4. Now factorizing here, 1 upon 3k plus 1 into here 3k plus 4, showing its factors inside. 3k square plus 4k plus 1, 3k square plus 3k plus 3 plus 1, 3k common, k plus 1. So 3k plus 1 into k plus 1. So these are factors of this expression put in here. 3k plus 1 into k plus 1. Reason for this step. And hence this is cancelled. So k plus 1 upon 3k plus 4. Now see here, we want RHS for n equal to k plus 1. So we want to set here n equal to k plus 1. So to set it according design, here k plus 1, This 3k plus 4 we show as 3k plus 3 plus 1. 4 expresses 3 plus 1. So therefore, p plus 1 upon, from this part, 3 common, k plus 1 plus 1. Now look here, this result is okay. In place of n, k plus 1 is okay. So it is RHS. So LHS is equal to RHS. Therefore, P of k plus 1 is true. Therefore, P of k is true implies statement is true for k plus 1. So Pn is true